This second section, we're going to be talking about empiric formulas, molecular formulas, and percentage composition. This definition of percentage composition rotates around the idea of mass, and you need to make sure you keep that in mind when you think in terms of percentage composition. So the percentage composition by mass is the percent of each element that's available or makes up a compound. So the percent of any particular element in that compound is the mass of the element divided by the mass of the compound times 100. So there's two ways to compute this. First is using experimental masses from experiments, and second is from the chemical formula using molecular or mole ratios. So let's take a look at some examples. Here's one where we do an experiment and we say that a compound has 1.04 grams of potassium, 0.7 grams of chromium, and 0.86 grams of oxygen. What's the percentage composition? Well, first of all, you have to add all three up so you know the total mass. So if you take 1.04 plus 0.7, that's 1.74, plus 8.86, that's going to be 2.60. So the total mass is 2.60. You have to have that first. The percent of potassium is that mass of potassium divided by the total. The percent chromium is the mass of chromium divided by the total. The percent oxygen is the mass of the oxygen divided by the total. And then you multiply the three, each one by 100, and that gives you the answers in terms of percentages. 40, 26.9, and 33.1%. And this should always add up to 100 or close to 100. Now, how do you calculate percent composition from the formula mass that we calculated last week? What's the percentage composition of C2H5OH? Well, the total molar mass is 12 times 2 for 2 carbons plus 1 times 6 for 6 oxygens. In case you missed it, it's 5 plus 1 here. 6 hydrogens, I meant. And then 1 oxygen at 1. So the total mass is 46. The formula mass is 46, or molar mass is 46. The percent composition is going to be the total carbon contribution to that. 12 times 2, or 24, divided by 46 times 100, or 52%. 6 divided by 46 times 100 for hydrogen. And 16, which is the contribution of oxygen, divided by 46 times 100, which is 35%. Now, an empiric formula, a couple of weeks ago I told you the empiric formula is the simplest formula of a compound. How do you go about calculating the empiric formula if you're given percentage composition? You take the percentage composition, or the amount of each element, and determine the number of moles of each element from its mass. You divide each molar amount by the smallest molar amount and find subscripts for the tentative empiric formula. You multiply the subscripts by something so that all the subscripts are whole numbers. So let's take a look at how we would do this. Here's what it looks like in a diagram. You have a mass of A and a mass of X. You divide by the molar mass of A and the molar mass of X, and you get the moles of A and the moles of X. Moles of A, moles of X. Then whichever one of these is smaller, you divide that into the larger one, and that gives you the ratio of A to X. And that mole ratio, once it's converted to smallest whole numbers, is the empiric formula. So here's an example. Let's say that you're given that a compound contains 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. Now, 1 mole of calcium is 40.1, So you have 0.337 moles of calcium. 1 mole of oxygen is 16, so if you divide that, you have 0.675 moles of oxygen. And 1 mole of hydrogen is 1 gram, and so you have 0.6678 moles of hydrogen. This is the smallest number, so you divide all 3 of these numbers by this, and you get 1 to 2 to 2. So your empiric formula is CaO subscript 2, H subscript 2. CaO subscript 2, H subscript 2, and you can rearrange this and write it like this, which is the formula for calcium hydroxide. Bacterial fermentation of grain to produce ethanol forms a gas, and the gas has the percentage composition of 27.29% carbon and 72.71% oxygen. What is the empiric formula for this gas? The solution for this is you assume that you have 100 grams of gas, because it's given in whole number percentages. If you have 27.29% carbon, then you have 27.29 grams of carbon. And 72.71% oxygen means you have 72.71 grams of oxygen. That's why you assume 100 grams. Then you divide by the molecular weight of carbon, which gives you 2.273 moles of carbon, and the molecular weight of oxygen, which gives you 4.544 moles of oxygen. This is the smaller number, so you divide both of these numbers by this number, and you end up with 1 to 2, or CO2, carbon dioxide. The molecular formula is the actual formula with the precise number of each atom in the compound. Sometimes the empiric formula is the simplest formula, but it's not the actual formula. So how do you find the molecular formula? To find the molecular formula from the empiric formula, once you find the empiric formula, you find out what the empiric formula's mass is. You divide the molecular mass that's given to you by the empiric formula mass, and it gives you a multiplier, which is a designated small case n here. And then you take the empiric formula and multiply it by that multiplier. And that gives you the molecular formula. So an analysis of a substance shows that it's 6.9899 grams of carbon, 1.1724 grams of hydrogen, and 9.309 grams of oxygen. What is the empiric formula? And if the molecular weight is 90.079, what is the molecular formula? Well, first, the empiric formula is found in this section up here. You take the mass of carbon divided by the grams per mole, and it gives you the mole of carbon. You do the same thing with hydrogen, gives you the moles of hydrogen. You do the same thing with oxygen, it gives you the moles of oxygen. Then you divide by the smallest number, and it shows you the empiric formula is 1, 2, 1. So here's the empiric formula, CH2O. Well, this empiric formula results in a mass of 12 plus 2 is 14 plus 16 is 30. So the empiric mass is right here, and you're given the molecular mass is 90.7, so the multiplier is 3. So you take this empiric formula and multiply everything in the empiric formula by 3. So the molecular formula is C3H6O3. Let's finish up by talking briefly about solutions. Solutions are a homogeneous mixture composed of a solute and a solvent. The concentration is the relative amount of solute in a given solution. Molarity is one way of measuring concentration, and it is defined by the moles of solute per liter of solution. Moles of solute per liter of solution. Vinegar is a solution of acetic acid, that's the formula for acetic acid, in water. If you have half a liter of vinegar and it contains 25.2 grams of acetic acid, what is the molarity of this solution? Well, from last week, you can calculate the number of moles of acetic acid. First, you find the formula mass of acetic acid. Then you divide the formula mass into the mass that you're given, and that tells you that that's the number of moles. So you have that many moles in half a liter, and the definition of molarity is the number of moles per liter, so you would multiply your answer by 2. So here it is, the moles per liter. You have 25.2 grams, which is what you're given. The formula mass or molecular mass of acetic acid is 60.052. You divide that out, and then you either multiply it by 2 or divide it by half. Either way, you get an answer of 0.839 molar, which is moles per liter. And it's designated by a capital M. Dilution is a process whereby the concentration of a solution is lessened by the addition of a solvent. On the left, you have a certain concentration of a substance or a solution, and you basically dilute it to half by adding an equal amount or an equal volume of pure solvent. And the molarity or the concentration on the left is twice as high as the concentration on the right. Now, the way to calculate this is the molarity of the first substance times its volume is equal to the molarity of the second times its volume. So the molarity of the graduated cylinder on the left is equal to its molarity times volume. That's the concentration on the left. The molarity on the right is equal to its molarity times the volume. So it's another way to think about it is in terms of initial and final volume. So generally in any problem, you're given 3 of 4 of these, and you just have to figure out the other one. So let me show you how to do that. If you have 0.85 liters of a 5 molar solution of copper nitrate, and it's diluted to 1.8 liters with the addition of water, what's the molarity of the new solution? Well, the concentration of the initial conditions are here. This would be 5 molar, and this would be 0.850 liters. This is what you don't know, and this is 1.80 liters. So to find this, you multiply these two together and divide by this. If you put the numbers in, you get 0.2 or 2.36 molar. Now there are other units that are used sometimes to express concentration. One is called a mass percentage. And this is the ratio of the components' masses in a solution's mass. So the component to the solution. For example, if something is 5% by mass dextrose, then that means it has 5 grams of dextrose to every 100 grams of solution. 5% means the mass, which would be, say, 5 grams divided by 100 grams of solution times 100. Volume percentage is the same idea, except you use volumes. So it's the volume of whatever you're mixing together divided by the volume of solution times 100. Volume percentage is much less commonly used than mass percentage. Mixed mass volume units are usually encountered in medical situations. So sodium chloride is given in a 0.9%, so that's 0.9 grams per 100 cc's of solution. That's what it means by mixed mass volume. This device measures glucose levels in the sample of blood. The normal range is given as milligrams, that's a mass, per deciliter, that's a. Parts per million is something, and parts per billion are two things that are used to measure things that are very low concentration. It's the ratio of solute to solution mass multiplied by 10 to the 6. So it's the ratio of masses. So it's a mass percentage, but it's multiplied by 1,000,000 because the mass of the solute is extremely small compared to the mass of the solution. And the same thing is true in parts per billion, except you multiply it by 1 billion instead of 1,000,000.